Okay, yes. Yes. Ready, ready.
So should I start?
Yes. Yes.
Okay. Okay. All right. So hello, welcome to our lecture. My name is Chibuzor Marcel, and I am affiliated with the Pan-African Citizen Science E-Lab. So here is the website of our organization in case you want to make inquiries about our activities. So today we are going to be learning about exoplanets. What are exoplanets? So in our table of content, I shall be introducing exoplanets, their history of discovery, method of discovering these exoplanets, their types, the instruments and the missions we use to discover these exoplanets. Then we'll talk about the habitability of these exoplanets, if they are able to have a life. Then I will talk about life as we know it, the search for life. Then I'll talk about rogue planets and some other facts about exoplanets. So what are exoplanets? Exoplanets simply means planets that orbit stars outside our solar system. So that term exoplanet simply imply extra solar planets, okay? Extra solar planets. So now, if I may ask, is the sun a star? Is the sun a star? And the answer is yes. The sun is a star, and we know that uh, our sun has planets. We are living on planet Earth. So does that also mean that the stars we see at night also have planets around them? So this is the question that would come into your mind when you start learning astronomy, when you come into astronomy and probably you learned the solar system. So, and we're going to answer this question. Could other stars have planets and life forms around them? So the, the, the first individual that documented his thoughts about this subject is called Bruno. He's an Italian astronomer in the 16th century. And remember, this 16th century was also the time of Galileo Galilei. However, they are just separate individuals doing their own thing, okay? So but much work was not done until the 1990s. So the first exoplanet that was discovered in 1992 by Alexandra and Day. So those exoplanets were orbiting a neutron star, or can simply call it a pulsar. You know, when I was talking about pulsars, I think I mentioned this. The first set of exoplanets that were discovered around a pulsar. But in 1995, just 3 years afterwards, Didier and Michel Mayor discovered the first exoplanet around a main sequence star. A main sequence star is a star that is still fusing hydrogen in the core to produce helium and heat. Now, in our Milky Way galaxy, the estimated number of exoplanets, so deriving from our knowledge of how these exoplanets are formed, they are pretty common. We estimated it to be around hundreds of billions. Hundreds of billions. In fact, they outnumber stars in our galaxy. Remember, the estimate of the stars, the maximum estimate of the stars in our galaxy is around 400 billion. So So you can imagine telling you that these exoplanets outnumber stars in our Milky Way galaxy. So they are very pretty much exoplanets that have been discovered is 5,741. This morning, I had to update the number because the number keeps increasing on daily basis. By tomorrow, 2 might be added, okay? So the number keeps increasing. And if you want to find out, you can go to the NASA Exoplanet Archive to search. So here you will see 5,690. That is a wrong figure, okay? But if you want to see the updated number, you come over to this side, you click it, then it takes you to the statistics. You see lots of other information about exoplanet discoveries there. So you could just simply Google NASA Exoplanet Archive to be able to get into this website. So methods of detecting exoplanets. We have these 5 major methods, 5 major. We have other methods, but these 5 are the major. So we have the Doppler technique, or can call it the radio velocity methods. We have the astrometry methods. We have direct imaging. Then we have transit methods, or transit timing variation, and we have gravitational lensing. But I want you to know something, that most of the discoveries that we are making in exoplanets are within our Milky Way galaxy. So I want you to know that. So talking about the astrometry methods, a moment. Talking about the astrometry methods, astrometry in astronomy simply means measuring the position and the motion of celestial objects, okay? That is just the meaning of astrometry. So in the context of exoplanet research, so we detect the tiny wobble in stars' position caused by the gravitational influence of an orbiting planet. So I'm going to play this simulation for you so that you can understand what I'm talking about. Let me pause it a little bit. Now here is a star, and here is the orbiting exoplanet around it. Now, for most cases, stars are far massive than their planets, okay? So, but that does not stop the small planets from influencing the massive star gravitationally. Okay, that does not stop it. So the two systems, this is a simplified situation. The two systems are going to orbit about a common center of mass, or can call it center of gravity. So they're going to orbit about a common center of mass. So that would make the star to appear to be shaking, okay? This picture is exaggerated, okay? Just to give you a sense of what is going on. So as that is happening, if you observe this star and compare it with the neighboring stars, you would notice that it is moving. There is a wobble. It is experiencing some movement around it. So if you compare it to other stars, there's some movement around it. So that is an indication that it probably has a planet, or even a white dwarf, or a black hole disturbing it, okay? So that is just it. So far, we have discovered, out of the 5,000 plus exoplanets that we have discovered so far, 3 of them were discovered through this process, this astrometry method. So you see the star is moving, it is wobbling relative to this other astrometry method. We have another method called the Doppler technique or the radial velocity method. It was pretty much like the astrometry method, but this time we are not interested in the wobble. We are interested in the light, the frequency of the light. So here we observe the star. It works through the Doppler effect, okay? Doppler effect states that when a light source or when a source that is emitting frequency is moving away from you, the frequency will reduce. So for light, we say it is red shifted. When it is coming towards you, the light will be blue shifted. When it is parallel to you, it will be balanced. So observe what is going to happen here. So astronomers use spectrograph mounted on their telescope to be able to detect this, because you won't be able to detect it with your eyes, but with some instrument, you'll be able to know that something is happening. There is some redshift effects going on. So far, out of the 5,000 plus exoplanets that have been discovered, about 1,093 were discovered through this process. And by the way, the first exoplanet that was discovered around a main sequence star in 1995 was discovered through this process called the Doppler technique or the radial velocity method. So the third method is direct imaging. Direct imaging. So this process works very well when the planet is farther away from the host star. When the planet is very farther away than the host star. For instance, let me use eclipse to describe it to you. During solar eclipse, okay, the moon blocks the sun, okay, to the point that you won't be able to see the sun again. But in reality, the moon is very, very small. In fact, it is insignificant when you are comparing the moon with the sun. But if, depending on their distance away, it can block the sun totally. So that's exactly the idea here. So we observe planets that are farther away from their host stars. So they block it. Now, the blocking is not only applicable for visible light, we can also apply it in the infrared spectrum, okay? Now, out of the many exoplanets that have been discovered, we have discovered 82. Out of the many, 82 exoplanets were discovered through this method. Then we have gravitational microlensing. This is how it works. When you are observing something, when you are observing a star, let's say a star, and a massive object passes through your line of sight, okay, what you would notice is the light source is going to be magnified. It's going to be amplified, okay? So when that happens, know that something massive has passed through. Planets can do that. Stars can do that. Black holes can do that. Every massive object in the sky can do that. So we call it gravitational microlensing. So let me play this simulation for you. Here you have a star that is radiating light, and you are here. Here you are. Here's the telescope. I hope you can see that little dots there. You are observing it, okay? But as you're observing this, the light is getting brighter. And you can see the light curve brighter and brighter. But as soon as that object, let me restore it back. As soon as that object, so the light curve is, observe the light curve, it is just, showing that there is an amplification, but as soon as it passes through your telescope, there is a little blip here, a little blip. Normally, this blip ought not to be there. It's supposed to just be smooth. Okay, but because this star has a companion, which is an exoplanet, that is why there's a blip. So that exoplanet has caused an additional increment in the brightness. Okay, so that is how we detect exoplanet through micro lensing. So we have discovered up to 223 exoplanets through this method. Up to 223 exoplanets through this method. So then we have the transit timing variation. This is the most popular and the most useful of all the methods. So let me play this video. It has to do with reduction in the brightness of light. Reduction in the brightness of light. Let me explain it better. If you have a bright source, if you have a light source, and maybe let's say an ant or a fly flies across it, you may not be able to notice it with your eyes, okay? Because the light is too bright. So even a little object, a little insect cannot make you to detect that it has actually passed through. But with equipment, you should be able to know that there was a reduction in the intensity of light. That's exactly this method. Now, let me play this video. As these planets transit, you look at the dip there, it causes a reduction. But the well of this one is deeper than the well of this one. This is because this exoplanet is more massive. So this method can even tell us the size and even the mass of these exoplanets. The more massive ones are going to block more light than the less massive ones. So this method is the most useful of all the methods. So if you look at the numbers, about 4,200 plus exoplanets have been discovered through this method. Then we have another case for when you have a multiple exoplanet system. You have more than one exoplanet system, you're going to see the light curve. It's going to be a little bit complicated. So the first exoplanet has passed through, okay? Then the second, then the third. You see the light curve? So the kind of light curve it makes. So that is for the timing, transit, timing variation for multiple transiting exoplanets. So types of exoplanets. To understand the types of exoplanets, let us first of all do some revision on the planets in our solar system. Remember, when I was lecturing on the planets in our solar system, I stated that the planets are divided into two. We have the terrestrial planets and we have the Jovian planets. And I also gave the general characteristics of the terrestrial planets and the Jovian planets. Remember that I stated that for the terrestrial planets, they are relatively small in size compared to the Jovian planets. Okay, now they are closer to the sun and they are made up of rocky and metallic materials. Okay, so they are denser. So that is why they are closer to the sun. So now for the Jovian planets, they are relatively large in size and they are formed further out. It is because they are formed from lighter materials, okay? Like the gases, like hydrogen and helium, okay? Hydrogen and helium measure composition of Jupiter and Saturn. Then we have the ice giants, which are methane, water, and ammonia. So that is just for the planet in our solar system. Now, bringing it into So using this to understand exoplanets, so far, the kind of exoplanets we have discovered are these. We have discovered terrestrial planets, the ones that look like the terrestrial planets in our own solar system, okay? Rocky, metallic, solid, high density. Then we have discovered gas giants just like Jupiter and Saturn. And we have discovered some weird other planets. We call them super Earths and mini Neptunes. And I'm going to describe them. Now, for the gas giants, okay? So gas giants, the reason why they are called gas giants because they are
Marcel.
size of Jupiter and Saturn, just the range of sizes of Jupiter and Saturn. And just like them, they're made up of hydrogen. Now, from the observation, are closer to their host stars, and they are called hot Jupiters. We call them hot Jupiters. I'm going to explain to you why they are called hot Jupiters, because they are so tightly bound to the star, to their host star, very, very close. Now, to explain how close they are, I want you to understand the star is between 2.2 to 15 million kilometers. Now, compare that with Mercury, our own Mercury, because Mercury is the closest planet in our solar system, and the distance is just 58 million kilometers. So compare the two. Okay, let's just take the maximum distance, 15 million, compare it with 58 million. So you see that these gas giants are very, very close to their host star. So we call them hot Jupiters. Now, hot Jupiters are easier to detect, okay, because they are pretty closer to their host stars and could make complex and can make complete rotations once in few days. Now, like I told you, the first exoplanet that was discovered in a main sequence star was discovered through astrometry method. Now, that exoplanet, it's a hard Jupiter, okay, to be specific, it's a hard Jupiter. All hard Jupiters are gas giants. You understand? So, but not all gas giants are hard Jupiters. Some gas giants are still further out, but it is very hard to detect those ones because their periods are running in tens of years. So, but because these hard Jupiters, their periods are within few days, we can easily detect them. Now, there's another exoplanet called Kelt 9b. It is the hottest the hottest gas giant or the hottest exoplanet ever discovered. It is hotter than some stars. It's hotter than some stars. So here is a simulation. So here is just showing you these gas giants. This is an artistic picture, please. All the pictures of exoplanet that you see online are artistic. None of them is real. None of them is true. Just take note. So they are artistic. Okay. So this is describing how these migrate towards the center. Sorry, migrate closer to the host star. So what this is describing is this. When they started forming, okay, there were debris in their disk. Okay, these debris are acting as stops, as brakes. So over time, they lose their orbital motion, their orbital energy. So they spiral in. Okay. So another factor is their interaction with other planets in the orbit. So they could transfer their energy to these other planets, and that will make them to drift inside. They will transfer that will make them to drift inside. So that is why, that is just one of the theories why they are formed. Interrupted, I was trying to explain something that is happening here. So I said the distance we have seen for these hard Jupiters, the minimum is about 2.2 million kilometers. However, if they drop much closer to the host star, the tidal force of the host star is probably going to tear them apart. So they're going to be torn apart and be destroyed. Then we have another one is Neptunian exoplanets, just like the how the name sounds, Neptune. So Neptunian exoplanets are similar to Neptune or Uranus in our solar system in terms of size, in terms of distance from the star, okay? And they are also composed of, the atmosphere is also composed of hydrogen and helium. And it may also contain water, ammonia, and methane. But this is just theory, okay? We have not really studied them very well, okay? Now, they are not called ice giants. They're not called ice giants, just like we call Neptune ice giants, okay? Because we have not really understood their composition. We have not really understood. So we just call them Neptunian exoplanet because they look like Neptune. Now we have some set of Neptunian exoplanets we call mini Neptunes, because they are smaller size than Neptune, but bigger than the Earth. Then we have the terrestrial exoplanets. The terrestrial exoplanets. So just like we have terrestrial planets in our solar, terrestrial exoplanets are Earth-sized or smaller, okay? Because in terrestrial exoplanet, we're talking about Mars, Earth, Venus, and Mercury, okay? So these planets, in the terrestrial exoplanets in our solar system, Earth is the biggest, okay? So for the exoplanets, there are those planets that are the same size or as Earth and less. You understand? So, and they're also mostly made up of rocks and metals, okay? So now, some could possess oceans and other signs of habitability. So if you're looking for life, if you're looking for extraterrestrial life, you should search for them in in terrestrial exoplanets. So now, some of these terrestrial planets orbit are different from their orbit in what we call the habitable zone. I'm going to explain that in the next couple of minutes. So some of them orbit very, very close, okay? So we call those one close-in terrestrial planets. So they range from 0.01 to 0.1 astronomical units. Remember, astronomical unit is defined as the distance from the sun to our planet Earth. So that is a standard. So you can imagine a distance of 0.01 to 0.1 AU. So that is for close-in terrestrial planets. Then we have Earth-like distances, which is from 0.5 to 1.5 AU. Then we have distant terrestrial planets, which is above 1.5 AU. So if you are looking for any terrestrial life forms, extraterrestrial life forms, should be focusing on those ones that are in the same distance as the Earth, just like our sun. Now, for their period, the period of those ones that are innermost into their host stars are less than 10 days, but for those that are at the same distance as that of Earth, have almost the same period as Earth, which is 365 days, and those ones that are further out, their period is few years to several decades. Then we have super Earth. Super Earth. So these super Earths are those exoplanets that are twice the size of Earth and up to 10 times its mass. Okay, those planets, there are some planets that are twice the size of Earth, so we call them super Earth, and there are very, very many. So the super Earth status is not because of their size compared to that of Earth. Okay, okay. So the reason why we call them super Earth is merely because of their sizes. Sorry, it's merely because of their sizes and not due to their composition, because they may not have the same composition as Earth, just because of their sizes, just 2 times the size of Earth. They could be composed of hydrogen and helium, but the size of Earth. So we call them super Earth. So here is a statistic that summarizes all of those types of exoplanets. So the most abundant is the Neptunian exoplanets. They are 35%, followed by the super Earth. Like I told you, they are very, very common, 31%. So followed by the gas giants, then we have the terrestrial. So I pretty much expect this because terrestrial planets are made up of metals. Okay, and there are not a lot of metals in the universe. And this is taken off from statistics about 5,000 exoplanets, just roughly 5,000 exoplanets. So here is the instruments and the missions that have been used to observe and discover exoplanets. So starting from the early 1990s, a lot of ground-based telescopes and space telescopes have been set up to be able to study and discover these exoplanets. So the major countries are America and Europe. So we have Japan, but mostly America and Europe. So starting from the 1990s, we have the Hubble Space Telescope, the Spitzer, the Kurat, the Kepler, the TESS, many of them, even the James Webb Space Telescope. But the 2 telescopes that were designed specifically for exoplanet detection and studies are the Kepler and the TESS telescope. They are space-based telescopes. Also, the James Webb Space Telescope is also designed to do further studies on this exoplanet, not to make new discoveries. So here is the statistics of exoplanets found each year. So starting from, this is a 30-year statistics. So starting from 1992, the first time, the numbers have been increasing every year. So the maximum recorded were in 2014 and 2016. So this is for the number 2020. This is stopped in the year 2022. So I don't have the knowledge of the number for 2023 and 2024. So if you go to that NASA exoplanet archive that I showed you, I got this data from here. I got the total number of the exoplanets that have been discovered. I got the number discovered by Kepler alone. I got the number discovered by TESS, and the number discovered by other surveys, including the ground-based and the space-based surveys. So look at the statistics. So Kepler has discovered a ton of exoplanets, and TESS is catching up. So here is the Kepler telescope. This is how it looks like. So the Kepler telescope was launched in 2009, and it only worked for 9 years. So it stopped working in 2018. So it was able to detect exoplanets through the transit methods, okay? But it only focused in few patches of the sky, in few constellations, okay? The Cygnus, the Lyra, the Draco, which is just 0.25% of the total sky. So, well, it was able to discover about 2,773 exoplanets. These are confirmed. and about 1,982 are candidates. They are still undergoing, verification. One thing is, when this space telescope discovered these exoplanets, we use ground-based telescopes to confirm them, and we do that in our lab. So here is the Kepler mission. It was set to orbit the sun. It was sent to orbit the sun, and observe that it is focusing in one direction. So it is focusing in one direction as it is, taking measurements. And here is the test mission. It was launched the same year Kepler was retired. So it is still working up to today, and it detects exoplanets through this transit method also. Now, unlike the Kepler mission that only surveyed 0.25% of the sky, the test is designed to survey 85% of the sky. 85%. So far it has discovered up to 543 exoplanets, with about 4,646 that are still yet to be confirmed. So most of these discoveries and confirmation are coming from citizen scientists, and I'm urging you to get involved in this. Whatever you discover becomes yours. Whatever you discover becomes yours. So get involved in exoplanet confirmation. So observe that it is positioned. Let me bring it back. Observe that it is positioned to be at an angle of 45 degrees to the moon. Okay. So that's the orbit of the moon, and that other blue line is the orbit of the test mission. Now, it collects data at perigee. At perigee is the position at which it is closer to the Earth. Okay, it sends the data to the ground station and continues collecting data from the sky. So look at how it collects data. It is surveying 85% of the sky. So here is a simulation showing some of the exoplanets that were discovered by the Kepler and the TESS. So here is our solar system. You observe that the planets in our solar system are well spaced out. But when we look at these other exoplanets, they are locked. They are pretty closer to their host stars. And the reason is because their orbit is in few days or weeks. So that is why it is easy to see them. It is also possible that these other ones have long period exoplanet, but because it takes time. Just imagine Jupiter, Saturn. The period of Jupiter is 15 years. And the period of Saturn is, I think, 29 years. And the period increases as you move out. So it is going to be very hard for you to be able to discover those exoplanets with longer periods. However, we are improving our methods, and we have actually done that. So that is why you don't see much of those ones with longer period, like this one now. This one have longer period, but most of the ones we have discovered have short periods, and they are very close to their host stars. So how about habitability of exoplanets? Let us discuss habitability of exoplanets. Now, to be able to understand habitability of exoplanets, I want to explain the meaning of life as we know it. Life as we know it. The human body is made up of, in terms of chemical abundance, it is made up of 65% oxygen, 18.5% carbon, 9.5% hydrogen, and 3.3% nitrogen. Okay. Now, for the universe, the chemical abundance in the universe, okay? So hydrogen is the most abundant by 75%, followed by helium. Okay, but I'm not going to consider helium because helium is inert. Then we have oxygen. Oxygen just 1%. Neon. Then we have iron and nitrogen. Okay, but if you compare these two, if you compare the elements in these two, you will discover that human body is made up of elements that are very abundant in the universe. So understand this. The human body is made up of elements that are very abundant in the universe. So like the hydrogen, oxygen, and carbon. So they are the building blocks of life as we know them. So that is why we are very, very sure that if we see extraterrestrial life out there, they might be made up of these chemical elements. Their body could be made up of these chemical elements, the hydrogen, the oxygen, and carbon. And carbon in particular is very preferred. Out of all the elements in the periodic table, carbon is preferred because carbon can bond with multiple elements to form complex compounds. Carbon can bond with multiple elements to form complex compounds. So if you study your organic chemistry, you get to understand this. That is the whole idea of pharmacies, the pharmaceuticals. They make use of these things. So compared to other elements, so carbon is the most preferred. For the universe prefers to build with carbon, to build life with carbon compared to other elements. So, and then we have water, because water is made up of hydrogen and oxygen. So these three elements are very essential for life as we know them. So the reason why I am mentioning this is because I want you to know that water is essential for life as we know it, because water is it acts as a solvent for dissolving, so it participates in biochemical activities. I mean, water, it serves as a solvent for biochemical activities. So the Goldilocks zone. What is the Goldilocks zone? Now, having water in a planet is not enough. The position of that planet will determine the state of matter of the water. So if the planet is farther away, it's going to be frozen. It's going to be very cold. If it is it is closer to the host star, it is going to boil away and evaporate. But if it is in a particular zone, we call it the habitable zone, or we call it the Goldilocks zone, then it's going to remain liquid. So the Goldilocks zone is a region around any star. Every star has a Goldilocks zone. So this Goldilocks zone provides conditions that are just right, where the heat is not too hot or too cold for liquid water to exist on the surface of that planet. So for a sun-like star, the Goldilocks zone is between 0.95 to 1.37 astronomical units. Now, in our planet, Venus is the second planet from the sun, okay? So this Venus is at the edge of the inner habitable zone, while Mars is at the edge of the outer habitable zone. Now, this habitability zone depends on the temperature and the luminosity of stars, okay? Temperature and luminosity of stars. For stars that are very massive, remember, the more massive a star is, the more the heat, the more the luminosity. We have seen that from the Herschel diagram. Okay, we have seen that from the Herschel diagram. So look at this diagram. You see this massive star, the brightness and the heat is so much. So the Goldilocks zone is going to be farther out. So look at the size as the size of the temperature of the star decreases, the distance to the star also decreases. The distance of the Goldilocks zone also decreases. So that is the idea of this diagram. It is showing you for a massive star, high mass stars, the Goldilocks zones are going to be farther out. So other factors, now that we have determined that water is essential for life, and for our planet to have a life, it must lie within the Goldilocks zone. Is that all? There are other factors, so such as the star population level. Okay. Now, previously we learned about population 1 stars, population 2 stars, and population 3 stars. Okay. Population 1 stars are stars that are like the sun. Okay. They are the 3rd generation of stars. Okay. Now, these stars are metal rich. They are metal rich and they're able to form terrestrial planets. Okay. So if you're looking at, if you are an astronomer, you want to discover alien life, you must be looking at population 1 stars, not just any kind of stars. You must be looking at population 1 stars because they are metal rich. Oh, my video has gone. Let me check my video. Let me check my video, please. Okay, I'm back. So then the star size. Low mass stars have, like I've even discussed from the chart, low mass stars have nearer habitable zone, while high mass stars have further out habitable zone. Then you have to also ensure the planet's atmosphere. If the planet has thick atmosphere, it means it can retain heat. Probably it has greenhouse gases. It can retain heat to be able to warm up the waters. But if it has thin atmosphere, it won't be able to retain heat. So even if the planet is in the habitable zone and it has water, this water might be frozen if the atmosphere is thin. Then we have orbital stability. Now, if the exoplanet has orbit that is highly eccentric, note that the habitable zone is a circular area. It's a circle. It's a circular area. Let me show you again from the diagram. Look at it. It's circular around the star. So imagine that you have a highly elliptical exoplanet. So at some time, the elliptical orbit is going to move it away from the habitable zone, and once that happens, it might affect any forming life form in that exoplanet. So these are the things you have to ensure to be able to find life. So then we have other geological activities such as volcanic activities, plate tectonics, then even magnetic field. Very important, magnetic field, because magnetic field around planets helps to protect its atmosphere. Okay, just take for instance now, our planet Earth. Our planet Earth has magnetic field around it, and it is shielding us from the solar winds. Okay, solar winds usually blow away, strip away atmospheres of planets, including exoplanets. And here is how it works. Solar winds are charged particles, and I've talked about these charged particles. When they are in motion, they have magnetic field. So when they approach Earth, they interact with the magnetic field of the Earth, and that makes them to be drifted away. So they can't just pass through Earth's atmosphere. Once they are approaching Earth, they get drifted away. And so that is what preserves our atmosphere. Okay, so but for Mars used to have magnetic field around it, but over time it disappeared. And that is why solar wind was able to blow it away. And that is why Mars has little or no atmosphere. So these are very important factors for habitability of life. How about the search for life? So if you are searching for life, if you are looking at a planet, you look at the atmosphere of that planet, there are indications of life forms. There are some signatures you will see that will let you know that this planet probably has life on it when you look at the atmosphere. So we call that, so there are into two, we have technosignatures and we have biosignatures. So for the biosignatures, so we talk about chemicals, okay? For instance, if you're looking at the exoplanet and there are abundant oxygen and ozone is made from oxygen, it's an indication that some photosynthetic life forms is in that planet, okay? Then we also have methane. If there is a presence of methane in the atmosphere of an exoplanet, it's an indication that there are some biological processes going on in that exoplanet. Then we have other organic molecules like amino acid lipids and nucleic acids. So these are the building blocks of life. So the detection of such molecules in significant amount can be indicative of a biological life. And here's a picture taken, here is just a chart from an exoplanet, WASP 39b. We are suspecting that this exoplanet has life in them because of these signatures. It has sodium. These chemicals that I just mentioned are just a few. We have others. So it has sodium, it has water. Water is essential for life. It has carbon monoxide. It has some sodium dioxide. Okay? So this is just one of the, we call it biosignatures. Then we have technosignatures. Technosignatures are indicators that may provide evidence of advanced extraterrestrial civilization. Number one of them is radio signals. Okay, so for any intelligent life out there that is advanced technologically, they should be able to be sending us, they should be curious enough, like the way we are curious of detecting extraterrestrial life, they should be curious enough to send us signals, maybe radio signals, okay, because radio signals, they go pretty far into the universe. So we should be able to collect them with our dish, radio dish. Now, during the time pulsars were discovered by Jocelyn Bell, we thought that aliens are trying to communicate with us because of the precise period of these pulses, radio pulses, okay? But that claim, we call it the little green man, okay? But that claim was dismissed when we discovered numerous other pulsars. But that is just number one way intelligent life should be able to communicate to their fellow intelligent lives. Then we have the Dyson sphere. So in this idea, we believe that any advanced civilization should be energy hungry. They should be energy hungry to the point that they could harness the energy of the sun. So they would do that by building a Dyson sphere, just a structure like solar panels, okay, around that star, okay. So like what you see here, just a structure around that star to be able to harness the entire energy of that star. So we call that the Dyson sphere. So we have another one, we call it Dyson swarm. So the problem with this Dyson sphere is in space, if you push an object, it continues moving. So what if something bobs it from one side? It might move, okay, while the star remains at the center. So it might potentially hit the star, it is going to screw up the whole project. So, but the idea of Dyson swarm is much better. It is just like satellite, the way Elon Musk is mounting satellites around Earth. They just built some solar panels around the sun to harness the energy of the sun. So that is how we detect it. Now, to be able to detect this, we are going to be perceiving some infrared radiation leaking from this Dyson sphere, okay? some infrared radiation should be leaking. So if we discovered a leakage in infrared radiation from a source where we are not seeing any light, starlight, that means an intelligent civilization might have engulfed the star using their technology. Now, the problem with this Dyson sphere and Dyson swarm is you need some materials, maybe planetary materials to build them. But if you look at this, the size of our sun compared to the size of these planets, even if you turn the whole planet into a material, it won't be able to overwhelm the sun. So it means that those extraterrestrial life should bring their foreign materials from their own world to be able to, have enough materials to build a Dyson sphere or a Dyson swarm. So another evidence for that is the unusual orbital patterns. Unusual orbital patterns. In 2017, an extraterrestrial object visited us. This object is called Oumuamua. It visited us from another solar system. So when it was approached, we thought it could be an alien coming to our planet. It could be an alien, okay? Probably they want to use our sun as a gravity axis to continue going to wherever they are going. They are traversing the whole universe, the whole galaxy. Who knows? But I don't think they are, but who knows? Then we have artificial illumination, star, city lights. So if you're observing an exoplanet and you see city lights, artificial lights, it's an indication that an extraterrestrial, an intelligent extraterrestrial life is based on this exoplanet. So these are just the few evidence of technologically advanced civilization as a techno signature. Then, now let us discuss about rogue planets. What are rogue planets? Rogue planets are planets that run away from their family. Okay, so let me define it. Rogue planets are celestial bodies with a mass similar to that of planets, but are not orbiting any star. They are just moving in the vastness of the universe. They're just moving there. So they wander through the interstellar space unearthed by any solar system. So where do they come from? How do they form? So this is an artistic image of a rogue planet. So they come from two processes. We have ejected planets, or what we call in situ formation. Now, in the ejected planets, we have 5 or 4 processes. It could be from gravitational interaction with other planets. Okay, now this is a star system, and you have 2 planets around them in the star, orbiting the star. Probably this one here, the inner one is bigger than this one. Let's just assume. Now, they interact gravitationally and they exchange energy, okay? In some cases, this one could extract so much energy from this inner orbiting exoplanet and would flip, go into, just move. It will acquire so much energy that it could escape the gravity of the sun. So that is through gravitational interaction with an orbiting planet, a co-orbiting planet, or even a passing star. So you can see 2 stars that are just passing, like pedestrian, but their gravitational influence could disrupt the planets in their orbits. So that could toss the planets away into the universe. So we have rogue planets can also come from supernova mechanisms. So you have a high mass stars because they are the ones that experience supernovae. So probably they have planets around them. When they explode, the shock wave, the energy, and the material that is tossed away could, potentially toss these planets away, and they will become rogue planets. These planets could become rogue planets. Another one for low mass stars. Low mass stars do not explode into supernovae. However, they shed their outer layer to become white dwarfs, remember. So when they shed the outer layer, their core remains. So their total mass will reduce. So to adjust, the planets have to adjust by moving into outer orbits. That is just the physics. They're going to move into outer orbits. So probably the orbit they might migrate to may not be able to bring them back to the star anymore. So they move into the universe as rogue planets. Then some stars somehow disappear. They just disappear. We call them disappearing stars. That will send all the exoplanets in that star packing. They will just go their different way. Then we have the in situ formation. Let me describe this in situ formation to you. You can understand it because we have actually described it before. Remember, when I was talking about star formation, I said stars are formed from the collapse of giant molecular clouds, right? Now, when they are falling inwards, okay, they experience friction. They are forming into a structure, so there is internal friction going on. So that friction generates heat, and that heat is trapped. And that heat increases the temperature of that system. We can call it the protostar maybe. Okay, but as soon as the temperature reaches 10 million Kelvin, hydrogen fusion will be ignited, right? I've talked about that before. Now, the same process, I also use the same process to describe brown dwarfs. And I said that brown dwarfs did not accumulate enough mass to be able to fuse the hydrogen at the core. So they do not have enough heat at the core to fuse hydrogen to helium. So brown dwarfs are failed stars, okay? And I said that brown dwarfs, their mass range from 13 solar masses to about 13 Jupiters to about 80 Jupiters, okay? Now, for these rogue planets can also be formed through the same process, just collapse of the giant molecular cloud. But the only difference is rogue planets, their mass is not up to 13 Jupiters, okay? Just like the minimum mass of brown dwarfs, they're not up to that. So you have rogue planets, you have brown dwarf failed stars, and you have real stars. So that is the process of these rogue planets. So now these rogue planets do not fuse anything, they do not emit light, so it is very hard to detect them. However, everything that has mass has gravity. So we can detect them using gravitational microlensing. We can also detect them using infrared because everything emits infrared. You emit infrared, I emit infrared, even eyes emit infrared. Everything in the universe emits infrared, except an object that is at 0 Kelvin. But we don't have such thing. So far, there is even if 1 Kelvin, 0.0001 Kelvin emits infrared. Okay, so everything emits infrared. So we can use gravitational microlensing and infrared imaging to detect these rogue planets. So in the galaxy, we believe that we have more rogue planets than stars in our Milky Way galaxy. So there are very many rogue planets. They are not rare, but they are very difficult to discover. Okay, there are so many rogue planets. So if you have been thinking they are rare, they are not rare. There are so many. In fact, they might even be closer to our solar system, but because they do not emit a reasonable amount of energy to magnetic radiation, our equipment is not even advanced enough to detect those radiations. So we don't really get to see much of them. But however, we have discovered about 90. We have about 19 candidates of rogue planets, out of which we have discovered 2. So in 2013, one rogue planet was confirmed. It was discovered through direct imaging because it is emitting infrared radiation. The mass is around 6.5 Jupiter masses. Then in 2016, we discovered another one through gravitational lensing. So the mass is between that of Earth and Mars. So other facts about exoplanets. You might want to ask me, do all stars have planets, exoplanets? Do all stars have exoplanets? And my answer is no. But a significant amount of stars have exoplanets. So, and this also includes low mass stars, including brown dwarfs, to high mass stars, those stars that are in main sequence, I mean, not even main sequence, 20 solar masses, 30 solar masses. Even those dying ones, those red giants, those red supergiants, we have discovered exoplanets around them. So now another question that you might ask me is, do population 2 stars have planets? Population 2 stars are second generation of stars after the first generation of stars, because stars, the materials used to to make stars undergo a cycle. So the first cycle was population 3, the second cycle is population 2, and the present cycle, which is our sun, is population 1. So does this population 2 stars, do they have exoplanets around them? And the answer is yes. But also understand that this population 2 stars are metal poor. So you may not be able to see terrestrial planets around them, but you will very much see gas giants around them, because gas giants are mostly hydrogen and helium. So population 1 stars, including the brown dwarfs, are prepared for exoplanets. That's the summary. Now, how about when observing exoplanets, do we just observe any kind of star? Or do we look at the plane, the orbital plane of these stars where we could find exoplanets? And the answer is yes. You have to look at the orbital plane. You don't have to just look at, just imagine our sun. You are looking, okay, the sun is just here. This is the orbital plane of the exoplanets. My hand is the orbital plane. And you are looking here. You are looking here. Okay, you may not be able to see the transits, the planet transiting. And from the simulation that I just showed you, you saw transit. So the planet has to transit in the field of view, in the field of view of the observer or the telescope. So that will bring me to the end of my lecture on exoplanets. Thank you so much for coming and paying attention. I hope you learned a lot. Please ask questions in the comment section. I'm going to reply them. Thank you.